Hi there, everyone. Thank you very much for joining us today for our webinar on how to make better oscilloscope measurements, oscilloscope tips and tweaks. We thank you for your attendance and participation. If you have any feedback or other webinar topic suggestions, then please let me know by chat, or you can email me later at support@testforce.com. Before we get started, I'd just like to let everyone know that this webinar will be recorded and you will be receiving an email afterwards with the recording, so you can go ahead and share it with anyone you think would be interested or rewatch it if you'd like. If you're interested in any of the other webinars that we'll be hosting, or to download any of the free resources we have available, such as white papers or application notes, please go ahead and visit testforce.com/academy and you'll find everything you need right there. If during the webinar you have any questions, make sure that you ask them in the Q&A section in the right side menu bar, and Rich Markley from Rohde Schwarz will be sure to get to all of those questions as we come to the end of the presentation. And now, without further ado, let's jump right in where we left off last month and talk about oscilloscopes with Rich Markley.
So as Randy mentioned, we're going to talk about tips and tweaks to better oscilloscope measurements. And as part of the presentation, there's three key things that I'd like you to be able to walk away with. One of the first one is some oscilloscope tips to make sure you're making the most accurate measurements possible. And with that, we'll talk about different settings and how you want to get the most out of your oscilloscope. Next, we'll talk about some probing tips. So the oscilloscope is really only as good as the way that you attach to your device under test. And so we will talk through some tips and tweaks to make sure that you're getting the best measurements out of your probes as well. And then I wanted to finish up with, there's a lot of specifications for scopes, and I thought we'd talk through what do they mean and when do they matter, and in some cases they don't matter. And so a lot of the times you'll hear people talk about different parameters of oscilloscopes, and hopefully this will clear some of that up and let you know when you should care about them and when maybe you could not necessarily pay attention to those. So with that, we'll go ahead and dive in. As Randy mentioned, definitely feel free to type in questions, and I'll do my best to get to them at the end. If for some reason we don't have enough time, we'll follow up with them afterwards. Or if it may be too in-depth to go into in the amount of time that we have, I may skip it, but rest assured we'll follow up with any questions that you have outside of this as well. All right, so here's our agenda. As I mentioned, we're going to go through and we're going to talk about tips and tweaks, and as part of that, I wanted to create a measurement checklist. And so these are some just simple things and maybe not necessarily common things, but some simple things that you can look for to make sure that you're getting the best measurements possible. And then, as I mentioned, we're going to talk about some specifications and go through what they are and how they matter. A couple things that I am going to assume as we go through this. One is that you're fairly savvy with a digital oscilloscope. And what I mean by that is, you know what the scope is used for. I'm not going to go into that. You know how to control the scope, but the vertical controls, horizontal controls, those types of things are. We're not going to go into kind of the basics or the fundamentals of the scope. I'm going to assume that you already have that knowledge moving forward. And then finally, I've made this very generic, so it will work towards any digital oscilloscope, whether it's one that you already have on your shelf or one that you might be looking at purchasing in the future. I wanted to make this so it's something that you'd be able to take forward with you, whether or not you use RNS oscilloscopes. So with that, let's go ahead and dive in. First, we're going to start with, as I mentioned on the checklist, do you have enough bandwidth? And bandwidth, it's the #1 parameter for an oscilloscope. And when you're going and let's say that you're going to grab one off the shelf, or you're looking at purchasing a new oscilloscope, this is probably the first thing that you're going to look at is how much bandwidth do I need in my oscilloscope? And bandwidth is also a very big driver of the cost of the oscilloscope. And so oftentimes you might be trying to decide how much bandwidth can I afford for the budget that I have. And so with that, you want to make sure that you're buying enough bandwidth to get the most accurate measurements. And at the same time, you also want to make sure that you're not necessarily spending extra money that you may not have needed to. So with that, bandwidth is basically, it's a frequency at which a sinusoidal input signal, so a sine wave coming in, is attenuated by 3 dB. And so this is the specification that all oscilloscope manufacturers use. When they're talking about an oscilloscope having a certain amount of bandwidth, it's going to be with a roll-off that up to 3 dB down is going to be within specification. And so on the right-hand side here, you can see what that graph may look like on an oscilloscope. And basically, as you look through this, you can see that most oscilloscopes should have a pretty flat frequency response until they start to get near the bandwidth specification, and then they can roll off up to about 3 dB. And 3 dB means that you could actually have almost 30% of the signal attenuated. And in practice, what does that mean? Well, let's say we look at these two little diagrams here on the left-hand side. As we look at those, so first on the far left one, you'll see it's a 50 kilohertz sine wave, and there's no attenuation to that signal. And if we're using, say, a 300 megahertz oscilloscope, as you get closer to that 300 megahertz specification, it could be up to 3 dB down or up to almost 30% down. And so here you would see roughly a 70% of the signal, or about a 30% attenuation that comes along with that. So this is what we mean when we talk about bandwidth and how bandwidth plays into your measurements. And this is something that you should keep in mind. If you're going to be measuring near signals near the limit of your oscilloscope, know that those could be attenuated. And with that, let's talk about how do you determine how much bandwidth you need then to get the most accurate measurements. And there's a couple ways to look at this. So the first one is essentially the amount of bandwidth you need is going to depend on the frequency components of the signals that you're looking at. And so when we talk about a digital waveform, or something that is not just a sinusoid, or something that's not just a sine wave, it's going to be made up of a number of different harmonics. And so those harmonics are what give the signal its shape, and those harmonics are what you can use to determine how much bandwidth you're going to need. And so the typical rule of thumb that we recommend is that you look at the frequency of your test signal, and then you decide on either 3 to 5x that bandwidth or that frequency to make sure you have enough bandwidth inside of your scope. And if we look over here on the right-hand side, you can see the blue waveform is made up of several different harmonics. And in general, you get enough information in the first through fifth harmonic to be able to accurately reproduce the waveform. And so we don't typically recommend that you go beyond the fifth harmonic. But one thing to keep in mind there is there are some tips to know when you can get by with less and when you may need more. And we'll talk about that when we get into the specification section. But in general, the rule of thumb is you want 3 to 5x the frequency of your test signal for the bandwidth of your scope, and that'll give you the most accurate measurement or a very good measurement of your waveform. Okay, I wanted to give you a few examples of what we talk about here, because I'm typically more of an example type person, and I like to understand that a little bit closer. And so here's a number of different interfaces that you might be looking at. So everything from a fairly low-speed serial bus, something like I2C, up to a relatively fast signal, something like PCI Express Gen 2 that might run at 5 gigabits per second. With that, let's take the minimal one here. So I2C, it can be up to, let's say, 3.4 megabits per second. With that, the clock frequency of that signal is going to be 1.7 megahertz. And so there you can use that clock frequency then to determine how much oscilloscope bandwidth you're going to need. If you only care about the third harmonic, you can get by with 5.1 megahertz of bandwidth. If you want to see the fifth harmonic, you need 8.5 megahertz of bandwidth. Now, that's a pretty low speed signal. Almost any digital oscilloscope available today is going to give you enough bandwidth to be able to accurately reproduce that waveform. And if you look, when I talk about oscilloscope class, it's something that we call like a value-based oscilloscope. But most oscilloscopes are going to have plenty of bandwidth to be able to make that measurement accurately. As we move up, though, this is when it starts to get a little bit more difficult. And something like USB 2.0 may surprise you at the amount of bandwidth that could be required there. So USB 2.0 runs at 480 megabits per second. The fundamental frequency of it is running at 240 megahertz. And so if you want to be able to, again, accurately reproduce the signal, you're going to want at least the third harmonic, which would be 720 megahertz, or ideally the fifth harmonic, which would be over a gigahertz of bandwidth in your oscilloscope. Now we'll talk about when you can get by with less, again, when we get to the specification section. But this is, again, following that general rule of thumb, the 3 to 5x. this is when you'll want to be where you'd want to be in terms of bandwidth. We'll take one more quick extreme example here. PCI Express 2.0, it's 5 gigabit per second. Data rate, the clock frequency runs at 2.5 gigahertz. With that, for the third harmonic, you'd want 7.5 gigahertz. And for the fifth harmonic, you'd want an oscilloscope with 12.5 gigahertz of bandwidth. And these are generally going to be higher end oscilloscopes, particularly when you want to look at it from a real-time perspective. And so they're getting up into the tens of gigahertz of bandwidth for these. All right, so that was bandwidth. And again, that's probably the most common specification. It's the first thing that you're going to look at when you go to grab a scope off the shelf. That's probably the number one thing that you're going to want to consider to make sure that you're going to be able to accurately reproduce the waveforms that you want to look at. The second one, and I know this seems really basic and really common, but you'd be shocked at the number of times that I run into an oscilloscope user who says, you know, this isn't what I expected to see on the screen. And what had happened was they had turned on something like averaging, or they had turned on a different capability inside of the oscilloscope that affects the way the oscilloscope displays the waveform. And so it's always a really good idea. Once you pull that scope off the shelf, you know, you're not exactly sure how the previous user had it set up, always start with a preset or a default setup. And so most scopes, they will have a button on the front panel. Again, it might be called preset, or it might be called default setup depending on the scope. But it'll bring the scope back to a known good setting, and that's always a great place to start, and it's going to help ensure that you don't accidentally make a incorrect measurement when you meant to, when you didn't mean to. And as I mentioned, a couple examples of times where this may come into play. Perhaps the user before had turned averaging on, or perhaps they had specified a memory depth, and so the memory depth was limiting the sample rate on the oscilloscope. Again, pressing default setup, pressing preset will allow you to get back to a known good starting point, and then you can go from there to set up your measurements and make sure that you're getting the most accurate ones available. Okay, so that one was pretty straightforward. Again, preset button, default setup. The next piece is, this is where it starts to put a little more rubber to the road, and I half-jokingly say that, but in a lot of ways, the probe is kind of like tires on a car. If you are driving in on ice a lot, you are often going to be better off having tires that are properly set up for those conditions, and it's no different when it comes to the probe. So you really want to make sure you select the correct probe and you set it up to make the best measurements possible. And unfortunately, again, particularly if you're getting a new scope in or if you're pulling one off the shelf, you may not actually have the probes with the scope that you want. And if you're like me, you might have a drawer full of probes that you go pull a couple probes out of. And you want to make sure that you're setting it up to get the most accurate measurements there. So let's talk through a little bit of what that looks like now. There's three what I call key factors when it comes to how you want to probe and what being able to make the best measurements are going to be with those probes. And so there's three things that you'll want to consider is, number one, how are you going to attach to your device under test? And, you know, probes have tons of different accessories to make it easier for you to come down and grab the signal that you need. But you'll want to know, okay, if I use these accessories, how is it going to impact what I see on the oscilloscope display, and how is it going to impact what's actually happening on my board? Because the probe can actually have an impact on your board. And so that's the second piece. You really want to select probes that are going to have minimum of impact on your device under test. And so when we talk about that, we'll often talk about the loading of the probes and how that can come through and affect what your actual circuit sees on the board. And then finally, again, the adequate signal fidelity. So what we come down and probe, by the time it makes it back to the oscilloscope display, may be slightly different depending on how we probe. And so again, you just want to be able to understand what does that look like and what impact might that have. So again, I'm an example type person, and so I like to look at, okay, let's talk about a couple different examples and what they look like. And in an ideal world, you would have something that looks like the right-hand side. You have your transmitter, you have your receiver, or whatever signal that you are probing there, And within that, you have an original signal that looks perfect, nice square wave. You come down with the probe, and then after the probe, the signal looks identical. So what is being received at the chip down the line has no impact to it. And then what you see on the display of the scope looks identical to what you're probing on your device under test. Unfortunately, there is no ideal probe. There is no ideal method to come down without having somewhat of an impact. And so what you'll traditionally see is some sort of effect on your device under test. So again, we start on the left-hand side. You have what's coming out of the transmitter, and let's say in this case it looks perfect. But once the probe comes down, the probe is going to have some sort of impact. And so what the actual receiver sees is going to be impacted, and then what is displayed on the screen of the oscilloscope is going to be impacted. And what our goal here is we want to make sure that we are minimizing those impacts. So we know that there's no such thing as an ideal probe, but we can hopefully make it where it's going to have a much more minimal impact on both the signal itself on your circuit and on the oscilloscope's display. So let's talk about how we can go about doing that. So I'm going to talk through a couple different probes and what some of the tips and tweaks are to make sure that you're getting the best measurements out of them. Probably the most common probe is a passive probe. So most oscilloscopes are going to come standard with these. They're least expensive, they're very robust. They don't have any active components. They're basically a wire with an RC network. And so they're going to be one of the most common pieces of equipment that you pull out to connect to your device under test. But there are some things that you'll want to be aware of when you're looking at passive probes. And one of the first ones is the input impedance is going to decrease as the frequency of the signal you're looking at increases. And so what I mean by that is you're going to have some sort of input impedance curve. And if you're like me, particularly before I really got into oscilloscopes, I would get a probe and it would come in a little package, and there was a little booklet inside of that package. And generally I took that little booklet and the package itself and I threw it into a drawer and I didn't think about it anymore. But there's actually some really good information in that booklet. And one of those really important and good pieces of information is this impedance curve, input impedance curve. And what we're looking at here is a passive probe is going to have a very high input impedance. Most of them are going to be upwards of 10 mega ohms, but they're only going to be that at low frequencies. So as you start to look at higher frequency content, the input impedance is going to drop. And while passive probes, most of them are 500 megahertz, maybe all the way up to a gigahertz, as you start to go to those higher frequencies, the loading of the probe and the input impedance is going to have a bigger effect on your device under test. And so, for example, here we can see at 500 megahertz, we're down close to 50 ohms for the input impedance on those probes. And as you can imagine, that can end up having a very big impact as you attach the probe to your device under test. So if you've ever had a probe that when you plugged it on, your device under test quit working, that was probably caused by the input impedance of the probe. Or if you've ever had it where your device under test wasn't working and you attach the probe and all of a sudden it starts working, that again is probably caused by that. And so our goal here is to minimize that. And if we can't minimize it, then to at least understand what the impact is of that probe and what it might look like with your once you connect it. So passive probes, another key thing that you need to do with them is you want to make sure that you're compensating them. And again, you probably compensate your probes when you first get them with your scope, and that is absolutely the right thing to do. But again, if you're like me, you might be grabbing a scope and you might be grabbing some probes out of a drawer. And more than likely, the passive probes are going to work with your scope, but you need to adjust them to make sure that you're getting the most accurate measurement. And so probe compensation, it assures that you're getting good amplitude accuracy from DC to the upper bandwidth limit frequencies of the probe. And if you don't compensate it, it can affect things like amplitude and rise time. And a great example of that is on the right-hand side, you can see some different images of what a probe will look like when it's not compensated properly versus when it is compensated properly. And so in the top right-hand corner, you can see this probe had some peaking that was occurring. And so before it was compensated, you could see how this might affect something like a peak-to-peak measurement or a rise time measurement. In the middle waveform, you can see we've gone through and we've adjusted the low frequency components of that probe. This is going to give us a really accurate measurement as we can get with that probe. And then some probes will actually give you the ability to also make a high frequency alignment as well. And so down in the bottom right-hand corner, went ahead and did that too. And that'll have an impact, as I mentioned, on things like, in particular, rise time and making sure that you're getting the most accurate rise time for those probes. So what I would encourage you to do is just read the manual about your passive probes, understand what the impedance, input impedance curve looks like, and then understand what settings can you adjust on that probe, and go through, and each time that you hook it up to the scope, if you haven't hooked it up to that scope recently, or it might be a new probe, make sure that you adjust it to get the most accurate measurements possible. So the next thing I want to talk about is how do you attach to your device under test, and in particular when it comes to things like ground leads. So those passive probes I was just talking about, very common for them to have something that we call an alligator clip. And so there's a picture of one down here in the bottom left-hand corner, and those are super useful. They are very nice because they give you a good extension to be able to find a good ground. But there are, again, some limitations that you should be aware of when you're using those. And it might be that you have no choice but to use the alligator clip, and that's fine. But you should definitely know what sort of impact it can have on your signal. And so I wanted to give you a couple examples of these here. And as we look at them, on the left-hand side, I'm measuring a 10 megahertz signal. So this isn't even a very fast signal. Measuring a 10 megahertz clock signal. And with that, I'm using just, again, that alligator ground clip. Super easy to get over to a ground lead. But that long ground lead adds inductance. And with that added inductance, you'll end up seeing ringing on a fast transition. And so that's exactly what we're seeing in the picture on the left versus the picture on the right where I used a short ground spring ground lead. And so this is one of the small little wire wrap ground leads that you can push on to the end of your passive probe. It keeps that ground lead very short. And again, this might not be doable. If you don't have a ground near the signal that you're looking at, you may not be able to use one of these. But if you can see how well it cleaned up that ringing. And this is one of those cases where when I talked about an ideal probe, you wouldn't have this situation. But unfortunately, what you see on the oscilloscope display on the left-hand side, it's not actually something that's happening in the circuit. It's something that's being caused by the probe, and the oscilloscope, which all oscilloscopes will do, will show you the exact waveform that it sees, is going to show you that ringing. And so, again, you might think that ringing is inside of your device under test if you didn't understand the limitations of a long ground lead. Okay, so that's a quick overview of kind of probing best practices when it comes to passive probes. Let's talk a little bit about active probes. And so active probes, again, we talked about passive probes. They're very robust. They're very inexpensive. They are very common. Active probes are going to be a little less common. They are a very high precision piece of equipment, but there's a lot of benefits that come along with active probes. Number one, active probes can be used if you want to look at a very specific type of signal. So for example, if you want to look at current, there are current probes that are available that make it very easy to look at current in your device under test. Or if you have high voltages that you want to look at, oftentimes you can find an active probe. But even when it comes to making just a single-ended measurement, active probes have a number of benefits. And one of those is the input impedance of them is going to be significantly better over higher frequency. They also often have adjustable DC offset, and they will be recognized by the instrument. So passive probes, some will be recognized by the instrument, some won't. If you have an active probe and it's designed for your oscilloscope, it's going to be recognized by that instrument. The instrument's going to be set up for that active probe, So we'll set the attenuation factor, those types of things. For a single-ended probe, these will incorporate things like FETs, so field effect transistors, that, as I mentioned, they provide that very high input impedance over a very high frequency range. And in short, so in general, we typically recommend active probes for signals as you get above signals with frequency content above 100 megahertz. And I know you may say, well, my passive probe goes up to 500 megahertz of bandwidth. And again, it does, but when you look at that input impedance curve, just know that you'll end up having a bigger impact on your device under test than you might with something like an active probe. Now, of course, the drawback to an active probe is they are typically an option, and they do also typically, they are going to be more expensive than something like a passive probe because they do have a lot of capability built into them to get that that nice ability in them. But just know that that's going to be one of the benefits of having an active probe is seeing that higher frequency content and not having as big of an impact on your device under test. If we look at probe connection, again, active probes are going to have a number of different options when it comes to how you attach to your device under test. The same rules are going to apply to what we just talked about. The shorter the leads, the better you're going to be in terms of the signal fidelity and the measurement accuracy. So when you look things like a short ground pin with the pogo pin coming off of the amplifier, this is going to be a much better solution than something like using a mini clip or a micro clip or using a long lead for your active probe. Now again, sometimes you don't have a choice, right? So if you don't have a choice, it's fine. Just know that the limitations of using some of those longer leads and how it might affect what you see on the display of the oscilloscope. Okay, so as we go through our checklist, we've talked about, do you have enough bandwidth? We've talked about setting the scope up from a known good configuration. We've talked about making sure you have the correct probe and knowing some tweaks to make sure that you're getting the best measurement possible out of it. The fourth thing I want to talk about now is properly scaling and positioning the waveform on the display. And we're going to talk through a couple key things to keep in mind as you're doing that. Part of it goes into vertical resolution. So essentially what buckets do the sample points get put into on the oscilloscope. And then we'll talk about sample rate and memory depth as well, and making sure that you have all of this on the display of the scope to get you the best measurement possible. So let's start with the vertical portion of the oscilloscope. And when we talk about that, we're going to talk about an analog to digital converter. So all digital scopes use an ADC. Within that, it goes through and it samples the signal at different points, and it will convert those signals into a value that is stored, and that value that is stored is going to have a time and a voltage component to it. And how that value is stored and how it's measured and by the ADC is going to have a really big impact on how good of a measurement the oscilloscope can make for you. So when I talk about vertical resolution, you'll often hear it talked about in bits. And so most oscilloscopes use 8-bit ADCs. Some oscilloscopes will use more than that. But essentially what that's talking about is that's going to be how many levels or buckets the oscilloscope, the ADC, has to put the signal that they just sampled into. And so if you have 8 bits, you're going to have 256 levels to place those signals into, or 256 buckets across a display. And those 256 levels, they're going to be spread across your display. So your display from top to bottom might have 8 divisions or 10 divisions. With that, it's going to have those 256 levels roughly spread across those 10 divisions. As I mentioned, some scopes may have more than that. So if they have 10 bits, they're going to have 1,024 levels. If they have 12 bits, they'll have 4,096. If they have 16 bits, they'll have 65,536 levels. And as you can imagine, the more granular we can get there, the more accurate the measurement's going to be able to be. And so that is one of the benefits of as you get into higher resolution, whether it's higher resolution from the ADC itself, or we'll talk about some ways to get higher resolution out of something like an 8-bit ADC. And again, I'm kind of a example picture type person. So the blue signal is the waveform itself, and then as the ADC goes through, it's going to sample and hold till the next point, and then it samples again. And so these are those levels that I was talking about. You might sometimes hear them referred to as quantization levels. But that's where the oscilloscope, it has to put that sample point into one of these buckets. And so that's how it decides where it's going to put it into. So how can we make sure that we're getting the best use of our analog to digital converter, whether it's 8 bits or more inside of the oscilloscope? And one of the most common things that I see customers do is they will oftentimes, particularly if they're looking at multiple waveforms, they'll put the waveforms across just a few divisions, and they'll separate them along the display. And so what you end up with when you do that is you're only using a portion of the analog to digital converter for each of those waveforms. And the drawback to that is that you're not giving the oscilloscope as much of an opportunity or as many levels to be able to put that waveform into. And so typically what I'll recommend is you want to scale the waveform across as much of the display as possible without clipping. And when I talk about clipping, I mean you don't want the waveform to go off of the display, because if it goes too big, it can saturate the front end, and that will also impact your measurements. But to kind of put this into a numbers perspective, so here I've got an example of the waveform, and this waveform we've put across 2 divisions. And if this is an 8-bit oscilloscope, and we've got 10 divisions across it, when you were only using 2 divisions, what that means is we're only going to be using a little less than 6 bits of the analog to digital converter. And so the way the math breaks down on this is we've got 256 levels. We're going to divide it across those 10 divisions, as I talked about. You end up with about 25 levels per division. Well, if we're only using 2 divisions, we're only giving the ADC 50 levels to try to put that waveform into. And when you figure that out, that ends up being less than 6 bits of resolution. So you've wasted a significant amount of resolution on the oscilloscope display by only putting the waveform across a small portion of it. So again, encourage you to scale the waveform across as much of the display as you can without actually clipping the waveform. Okay, let's talk a little bit about ways that we could increase that vertical resolution. So I mentioned as you get up to 10 or 12 or 16 bits of resolution, you have more buckets to be able to put those sample points into. And there's a number of different ways that oscilloscopes can go about increasing their vertical resolution. And so one of those is averaging. And averaging is a very common technique. Basically, it takes a user-defined, so you can come in and you can tell it, I want you to average 2 or 10 or 100 waveforms, and it averages them into a single waveform through post-processing and puts that on the display. And that's going to increase the signal-to-noise ratio of the oscilloscope, effectively giving you more vertical resolution. The benefit here is it doesn't affect bandwidth. So we'll talk about some other ways to increase vertical resolution where you will lose bandwidth. And it also doesn't affect sample rate, so you're not going to have to worry about aliasing and those types of things. The drawback to it is, or the limitations to it, is it requires a repetitive waveform. So if you look on the right-hand side, I had a little I²C clock that was changing from a high to a low, and that's why that signal's jumping around. Is as I was trying to average it, you can see that it wasn't a repetitive waveform. And so you get something that is not the real waveform that you wanted to look at. Now there's some ways we can go through and get that waveform to be more stable through using something like an I²C trigger, but this was pretty representative of what happens if you try to use averaging with a non-repetitive waveform. And then the other drawback to it is, again, this is post-processed, and so all the noise benefit, the signal-to-noise ratio benefit that you get, it's not going to be seen by the trigger. So if there was a large amount of noise on the waveform, that type of thing that you're trying to remove, you could still have a little bit of trouble getting a stable trigger because this is processed after the fact. Another common technique to get more vertical resolution is something that's called high resolution. Most oscilloscopes call it high resolution. Some oscilloscopes will call it something like enhanced resolution. But essentially, it's often a boxcar average. And what it does is it takes extra sample points. So if your ADC is running at, let's say, 5 gigasamples per second, but you're at a sweep speed where you only have enough memory depth to be able to store a gigasample per second, well, now you have a bunch of extra sample points that you can use within the high resolution mode to get a increased signal to noise ratio. And the way this works is it'll take those extra sample points, it averages them together into a single point, it'll take the next set of sample points, average those into a single point, and as you can imagine, as you average those together, you get a much cleaner waveform coming out. So high resolution is a great option to consider when you want to get an increased signal to noise ratio and be able to increase your vertical resolution. And most data sheets of oscilloscopes will explain to you what type of vertical resolution they can get up to with these. So whether it's up to 11 bits, 12 bits, or all the way up to something like 16 bits. The benefits of this, it does work in single shot, so it doesn't have to have a repetitive waveform. There are some limitations, though. One, oftentimes the filter bandwidth is not explicitly known, and it really depends on the decimation factor. So you may not know exactly how much bandwidth you still have in your oscilloscope. And because essentially high res is a form of a filter, you may end up filtering out some signal content that you care about. It does require a sample rate reduction. So as I mentioned, we're using those extra sample points. And along with that, it does increase the chances of aliasing the signal. So if you reduce the sample rate too much, you could end up aliasing the waveform. And again, this is a post-process event, so the decimation occurs after the trigger. So again, the trigger wouldn't see that increased resolution. A third option is digital filtering. So again, this is where a type of basically low-pass filtering. It reduces noise, it increases that signal and noise ratio. For RNS scopes, this is done in an ASIC prior to the trigger. So one of the benefits is it is actually seen by the trigger, and you can get up to that 16 bits of resolution. Another way of going about this that is often used, and so this is a digital filter, you can use the analog bandwidth filter in the front end of the oscilloscope, and that will lower noise, and that will be seen by the trigger circuit. And almost every scope has some sort of analog filter in the front end, whether it's 20 megahertz or 200 megahertz or more. Okay, so we talked about the vertical portion of it. Let's talk about the time portion of it, the horizontal portion of it. So again, the ADC, it samples the points in time, and it puts them into, each sample point has a time and voltage component. The sample rate is going to be specified on the oscilloscope, and it's typically you want it to be 2.5 times higher than the bandwidth of the scope. And I'll talk about, again, where you have to worry about that and where you don't. But each of those samples are going to be spaced in time, and this is typically measured in something like samples per second. Almost every digital oscilloscope today is going to be measured in megasamples or gigasamples per second for those from the sample rate on them. And again, if we look, we have the blue signal, and as you go through, not only do we have the vertical component that we talked about before, those different levels, but then we also have the actual sample points in time, and that's the ADC. So basically, the resolution of the resolution and time of the ADC as it goes through for those sample points. What happens if you don't have enough sample rate? So everybody's probably heard of the Nyquist rule. If it's violated, you can end up aliasing your waveform. And the thing that's tough about aliasing is you may not always realize that you're aliasing your waveform. And let me give you an example here. So we've got an input signal. This is a gigahertz sine wave. But in this example, we're only going to be sampling it at 750 megasamples per second. And so as we go through and we sample this, we get sample points on the waveforms. But when the scope goes through, and again, the scope is, it's only going to show you what it sees. as it fits a waveform to that, you get something that looks like the input signal, but it's at a much slower frequency. And so in this case, it's at 250 megahertz. And so as you can see, this is the aliased waveform. And the unfortunate thing here is if you aren't paying attention to the frequency of that waveform, you may not realize that it was aliased. And so you always want to be paying attention to the sample rate of the oscilloscope and knowing how much sample rate you have for the amount of bandwidth on the oscilloscope that you're using. And so sample rate, there are two things that come into play there. Clearly, the sample rate of the ADC is going to be the maximum sample rate, real-time sample rate that you get. But then there's also, we have to have a spot in memory to be able to store this in. And if we capture a long period of time at a high sample rate, that takes a lot of memory to be able to store that. And so as the ADC goes through and digitizes this, it gets stored into memory. And this memory is what we talk about when we talk about the memory depth of the oscilloscope, or the acquisition memory depth of the oscilloscope. And there's a pretty simple equation that will tell you the relationship between the sample rate of the oscilloscope, which is over here on the left, the record length or the memory depth of the oscilloscope, and then the amount of time that you want to be able to capture. And the amount of time is basically what the time scale is. So are you at 10 nanoseconds per division or 10 microseconds per division? And then how many divisions across the display there are. And so as you go through and you multiply this out, this will tell you how much memory depth you need. So if you're at 100 nanoseconds per division, that's a pretty fast sweep speed, and you're sampling at 10 gigasamples per second, you only need about 10 kilopoints or 10 kilosamples of memory depth. It's a pretty small amount. But as you get to longer time scales or longer sweep speeds, say 100 microseconds per division, if you want to maintain that same sample rate, you're going to need an oscilloscope that has 10 megapoints or 10 megasamples of memory. If your oscilloscope has less memory than that, the oscilloscope has to start dropping the sample rate. And as it starts to drop the sample rate, that's when you want to be paying attention to make sure you don't alias the waveform. Okay, so we went through, do we have enough bandwidth, preset, default setup, getting the right probe, properly scaling, and making sure you're paying attention to the way that the oscilloscope is set up. Now, I want to jump into, we've talked about a bunch of different specifications here, and if you've bought an oscilloscope in the last 5 or 10 years, you've probably paid attention and looked at a number of these different specifications. And I wanted to go through the specifications and just talk about, in reality, when they matter and when you need to pay attention to them and when you may not need to pay attention to them. And so let's start with bandwidth. We talked about the 3 to 5x rule, that you want the third or the fifth harmonic to accurately represent the waveform. Bandwidth is specified in hertz, so it's megahertz or gigahertz. With that, so when does it matter? In general, I would say this is a pretty hard and fast rule if you want to get the best signal integrity. So particularly if you're looking at digital signals, you want to see the actual frequency content of those third and fifth harmonics. The rule of thumb that I talked about here, this is a pretty basic rule. There is also other ways to determine how much bandwidth you need. One of the most common ones to go along with that is also looking at the rise time of the fastest edge in your signal to determine how much bandwidth you'll need in your scope. So when does it not matter? There are a couple exceptions. So if you're just looking at a sine wave, you can go up to the bandwidth of the scope because theoretically there's no additional harmonics there. And so if you're looking at a gigahertz sine wave, you can get by with a gigahertz oscilloscope. Just recognize that it may be attenuated by up to 3 dB. So as we talked about, that roll-off of the oscilloscope as it goes down. The second one is you're using the scope for protocol analysis, and what I mean by protocol analysis is you're doing protocol decode of a waveform. In general, you can typically capture and decode at rates up to the bandwidth of the scope. And the reason I say that is when we're actually decoding the waveform for you, we're just looking at where that threshold crossing is. And so whether it's a sine wave crossing that threshold because you don't have any of the additional harmonics, or whether it's the actual square wave signal itself, it doesn't matter as much for the decode. Now, if you want to, of course, correlate back and look at the signal integrity aspect of it, that can require you, again, to go back to the rules of thumb that we talked about. Okay, so that was bandwidth. Sample rate. So when we talk about sample rate, we talked about we want to have a minimum of 2.5 times the bandwidth of the scope. But sometimes you actually need a little bit more than that, and it all depends on what the roll-off of the oscilloscope is. And by roll-off, what I mean there is once oscilloscopes get to their bandwidth limit, so again, let's use that 1 gigahertz bandwidth limit, some oscilloscopes have a Gaussian roll-off, which they'll roll off relatively slow, and so it'll step down pretty slow as it goes to higher frequencies. And some scopes will have a much sharper roll-off, sometimes called a brick wall roll-off. And that's going to determine how you decide how much sample rate you need. Now, I will tell you, not every manufacturer is going to say what type of roll-off they have. In general, you can trust the manufacturer that they are making the right decision for the amount of sample rate. And so I wouldn't concern yourself too much with that. Just know that they know to make the most accurate measurement how much sample rate they're going to need for the roll-off of the oscilloscope that they have. Again, this is specified in samples per second. It's typically going to be megasamples or gigasamples per second. When does it matter? In general, it's a pretty hard and fast rule. There is one benefit of extra sample rate, or one kind of high-level benefit of it, and that is for that high-resolution mode where we talked about the extra samples can be used to increase vertical resolution. So that can be a nice benefit of having extra sample rate, particularly if you can control the sample rate and turn it down, or if you can use memory depth to turn it down so you can get a high-resolution capability at faster sweep speeds. So when does it not? So as I mentioned, how do you know when you can get by with it? It really depends on the roll-off. And again, you can probably trust the manufacturer is going to take good care of you here. And then the last point is, keep in mind those extra sample points, they do have to go somewhere. So oftentimes it'll require extra memory for the higher sample rates to make sure that you can capture an equivalent window of time to a slower sample rate. Memory depth, so this is, again, memory depth, acquisition time, sample rate, are all directly related by that equation. You'll often hear it talked about in terms of points, so kilopoints, megapoints, gigapoints, or samples, kilosamples, megasamples, gigasamples. When does it matter? So in general, the more memory, the better. It allows you to maintain that maximum sample rate for longer. There are some caveats and tips, though. So some scopes will slow down if they're working with deeper memory. And in fact, some scopes will default to a small percentage of the available memory to keep the scope responsive, and you have to go in and turn on additional memory. I always encourage you to try out an oscilloscope before you buy it to see if it is responsive enough for what you expect, particularly if you're going to be buying one that you need for a fast update rate, which we'll talk about here in a second, and also with deep memory. Keep in mind the maximum memory specifications can be misleading, and what I mean by that is some scopes will trade off memory when they're in run mode versus stop mode, or if they're using digital channels, or they'll interleave between channels, and they'll talk about the maximum memory when it's interleaved. So that will oftentimes be specified in the data sheet. It's a simple thing to take a quick look at. And then using something like a history mode or a segmented memory capability can greatly extend your capture time for bursty signals. So if you have a signal that has a bunch of idle time, if you go through and digitize that, you're basically wasting memory on part of the signal that you probably don't care about. Segmented memory or history mode allows you to skip that idle time, and so you can more efficiently use the memory of your scope. So when does memory depth not matter as much? If you're looking at really fast sweep speeds, deep memory probably isn't going to matter. So if you're in the nanosecond range of sweep speeds, even when you're at 10 gigasamples per second sample rate, as we talked about before, you're only going to need 10 kilopoints of memory to be able to keep that same sweep speed or to keep that same capture time. And so almost every digital oscilloscope is going to have that amount of memory depth with it. But if you are going to be capturing longer periods of time, that's when that deep memory really comes into play and is beneficial. Vertical resolution, so again, it's often quantified by bits you'll hear people talk about. Most scopes, again, 8 bits, there's ways to get them higher. Some have 10-bit ADCs, etc. When does it matter? So again, in general, the more resolution, the better. But where it really comes into play is if you're looking at a small signal in the presence of a larger signal. So example, you're looking at ripple on top of a power supply waveform. That can be really difficult if you don't have enough buckets to be able to put those waveforms into, because those little ripples will just get forced into a single bucket. So that's where it really has a big benefit. There is also a side benefit, and that is scopes typically have, with more vertical resolution, also have typically lower noise. And that's almost a necessary benefit, because if you have a bunch of noise, you're just going to lose the additional benefit of vertical resolution and have it eaten up in the additional noise of the scope. So when does it not matter? So again, if you aren't looking at small signals in the presence of larger ones, or if you're buying a scope with that has a lot of resolution but has a lot of noise, you're really not going to get any benefit out of it. So speaking of noise, so all digital oscilloscopes have noise. It's an artifact of the system of the scope itself. It's typically specified in ACRMS, but it can sometimes be specified as a % of full scale, or just viewed in a peak-to-peak measurement. The peak-to-peak measurement is probably not the best way to measure noise, but it's probably the simplest way to measure noise. If you've ever taken a scope and moved it all the way to 1 millivolt per division, like we have down here in the picture, that's a really quick way to see how much noise an oscilloscope has, but it's not typically the way that it's specified or most commonly measured. So when does it matter? In general, again, it's a necessary evil of scopes, so it's always best to start with a scope with low noise. You don't want the oscilloscope to hide signal detail in its noise. There are some caveats and tips. Noise is directly related to bandwidth. So some scopes will artificially limit bandwidth to lower the noise, particularly at smaller volt per division settings. Some scopes make software expand to those lower volt per division settings, which will also software expand the noise. Using bandwidth filters, as I mentioned, is a great way to lower noise if you don't need all the oscilloscope's bandwidth. So knowing how much bandwidth you need can really come into play here. Those resolution enhancing methods that we talked about are also important. So when does it not matter as much? It's still going to matter, but at larger volt per division settings, for example, 1 volt per division, noise takes up a much smaller percentage of the overall graticule, so it may not be as noticeable, but it can certainly still have an impact on the device under test and your measurements. Update rate, so half-assed scope triggers, processes the information and plots it to the display. This is often called blind time, or dead time. It's specified in waveforms per second. So when does it matter? So if you're trying to find an infrequent event, fast update rate will definitely increase your chances of seeing it quicker. It can also help you find outliers in measurements faster. If you've ever left an oscilloscope running over the weekend with infinite persistence mode on, fast update rate would help with that. There are some caveats. So some scopes will specify a segmented memory rearm time as an update rate. It's not quite the same thing. Update rate is really when it's displayed to the oscilloscope display, or plotted to the oscilloscope display. And then some scopes will trade off memory depth for the ability to get a fast update rate. And just know, if you have to trade it off, know which one matters more to you. Is it more important to have that fast update rate, or is it more important to have deep memory? So when does fast update rate not matter? If you're only capturing single shot events, update rate doesn't matter at all, because you're only capturing one waveform.
That was great. Thank you, Rich, for presenting today and for the very informative webinar. I'd like to say thank you to all of our attendees today who made the time to sit in with us for this webinar, and for all of your participation. As I mentioned at the beginning of the webinar, it is being recorded, and we will send out an email with the recording in the next day. We have a new lineup of webinars coming up on our TestForce Academy, so visit testforce.com/academy, and we're always open to hearing your suggestions as well for different topics. So stay tuned and reach out if you have any questions or comments. you can send a message to marketing@testforce.com and we'll get back to you with any answers that you're looking for. We had a few questions come into the Q&A section, and we'll be getting back to you, possibly by email. Just some of them are quite specific. And I'm going to leave the chat window open for the time being in case anyone else has some questions that you'd like to ask. But if any questions come up later, then don't hesitate to either reply back to my email or send a message to marketing@testforce.com, and we'll get back to you. I look forward to hearing from everyone and hope that you have a great day. Thanks again. Take care.